we are going to discuss about all different power converters. All different power converters. You may still remember from the first class, okay? According to the fact that all the electric power or electric energy can be classified into two types. Still remember that? AC and DC, alternating current and direct current. There's two types. Therefore, we can classify all different power converters into how many types? 4 types, right? Between AC and DC into another form of AC or DC. So we are going to talk about these 4 different types of power converters in detail. And today we will start from AC to DC. AC to DC converters. And we also already mentioned that another name, another typical name or commonly accepted name is called rectifier. Rectifiers. We have an outline here listing all the topics we are going to discuss, but right now it's quite difficult for you to understand all these different names. So I'll just skip this. And we start from the very first power AC to DC power converter, which is called single phase controlled rectifier or single phase controllable rectifier. Single phase I've already mentioned to you. Single phase controlled or controllable rectifier. And there are all different kinds of power rectifier circuits. Okay, we'll also talk about this one by one. We're going to go through these different single-phase controlled rectifier. And the very first one is what we call single-phase half-wave controlled rectifier. Single-phase half-wave controlled or controllable rectifier. This can be considered as the simplest power converter. This is on the left-hand side, this is the circuit diagram of the single-phase controlled, a half-wave controlled rectifier. If you look at the left-hand side, you have, on the left-hand side you have, this is a U1, this voltage is actually coming from a voltage source, AC voltage source. Okay? You can consider an AC voltage source is connected to this terminal, these 2 terminals here. So the left-hand side representing the input energy side. So the input is AC. And what is the function of that transformer? Can you guess? Why do we put a transformer there? You will see this transformer very often in the future. When we have a power converter, usually we always have a certain transformer for each power converter. Why is that? Very often.
Reduce or enlarge the voltage.
Okay, that's probably one of the reasons. Through transformer, we can adjust the voltage level. If the input voltage is too high and the power converter, power semiconductor devices cannot deal with that high voltage, then we can reduce that input voltage a little bit through this transformer. Okay, what else? Can you guess? Isolation, right. Actually, I was going to put isolation as the first reason. We put transformer here, the primary reason is for isolation. Okay, in many cases, especially from AC to DC, or from DC to AC, the requirement from these two sides, I mean, there is a requirement from the input energy side, there is a requirement from the output, the load side. Usually, they require, if the input is AC, output is DC, or the input is DC, output is AC, then these two are usually two different systems, two different energy systems. Then they usually require you have isolation between these two different energy systems. Okay, so the primary reason for putting this transformer here is for isolation. Of course, they have many other functions. For example, he just mentioned it could be used to adjust voltage level. Okay? And then this input voltage source and transformer, actually, in the future discussion, we can always consider this equivalent to just an input AC voltage source. This is equivalent to just the AC equivalent source with the voltage level of U2. Okay, just using U sub 2 to represent the input side. Okay. And then on the right-hand side, you can see this AC to DC power converter is very simple. You have a thyristor here. Okay. And then in series of that thyristor, you have a load. Okay. This is the output side. The output, the load is just a resistor. So very simple. You have an input voltage source, you have a thyristor, you have a load. So almost the simplest power converter we can see. Okay? So let's see how this circuit is working. So this is the input voltage. If you look at the right-hand side, the uppermost waveform, this is the input voltage, sine wave. Okay? Sine wave AC input voltage. How does this work? If we start to analyze this circuit, do you have any suggestion how do we start to analyze? When you look at in a circuit, when you have some thyristors, how do we analyze this circuit? You have any idea? Let me give you a hint. when we talk about thyristors, when we talk about the characteristics, especially the static characteristics, did we mention the characteristics of thyristor is very similar to what? The most similar one is what? Diode, yes. That's the diode characteristics is very, very similar to thyristor. There's only one difference. The diode is uncontrollable. Thyristor, we can turn it on. We can determine when, at what time to turn on the thyristor through the gate. Okay? That's the only difference. But other than that, thyristor is similar, is the same as a diode. So in the future you will see, if you see a thyristor circuit, you can always start analyzing this circuit from a counterpart diode circuit. That means you can always start from replace this circuit from replace this thyristor with a diode, and you see how this diode circuit is working first, and then you can gradually understand when this is changed back to a thyristor how that is working. Okay, so let's start from here. How this diode circuit is working? Oh, that's very simple. You have a diode here. When the diode is subject to a positive voltage, then this equivalent resistance of diode is nearly zero. Therefore, this voltage is applied to the load. Therefore, there is current flowing this way. Okay. When this input voltage U2 is negative, then this diode will be reverse blocking, and the equivalent resistance of this diode will be very high, just like open circuit. Therefore, there will be no current flowing through. Okay, and therefore the on load, if you look at this load, the load voltage, very simple, would be when the input voltage is positive. This is U2. When it's positive, then load voltage will be the same as input voltage, because this diode is conducting. This terminal will be considered as short circuit to this terminal. So UD will be equal to U2. But when the input voltage is negative, this is U2, the diode will be blocking, no current flowing through. Therefore, the load voltage will be zero. Okay? Therefore, the load voltage will be positive, same as the input voltage. Okay? And when the input voltage is zero, then when input voltage is negative, then the output voltage will be zero. And then next cycle comes, positive again, and then when the input voltage is getting negative, the output voltage is zero. So that's very simple. This is called single phase diode rectifier or uncontrolled rectifier. Why is it called rectifier? Why can this be called rectifier? Input is AC, output is, this is DC, no negative voltage anymore. So that's called rectifier. And it's called single phase uncontrolled. We cannot control that. Rectifier. Okay? So once you understand this very simple diode circuit, we can see if we now change this diode into a thyristor, what difference do we make? Okay? This thyristor, changing this to thyristor, gives us the ability to determine at what time you turn this on, at what time you turn this switch on. If it is diode, we cannot determine. When you have input voltage positive, then it's conducting. But if we change that to thyristor, we can determine at what time to turn it on. For example, on the right-hand side of the screen here, you can see when the input voltage is positive, all right, just find a seat anywhere. Okay, when the input voltage is positive, although this thyristor has been already subjecting to positive voltage, but it's not turned on yet. It will be only turned on when we inject current into the gate of this thyristor. Okay, so for example, if for this period of time, let's see, I do not inject gate current yet. Therefore, there is no current flowing into the gate of thyristor. Therefore, the thyristor is not turned on. Therefore, this is still open circuit. This is not conducting. Therefore, the load voltage is still 0. No current flowing through. Until at this time instant, omega T1, if at this instant I inject a current into the gate of thyristor, now this thyristor, on one side it is subjecting to positive voltage, on the other side there is a gate current injecting into it. Therefore, those two conditions make this thyristor turn on. Okay? Therefore, at this time instant when this thyristor turn on, then this can be considered as short circuit, because when thyristor is turned on, the equivalent resistance is very short, very small. And therefore, this can be considered as short circuit. There will be current flowing through here. Therefore, the load voltage UD will be the same as U2. So you can see during this period of time, between omega T1 and pi, this load voltage is equal to, you see, UD is equal to U2. Okay. Until this is true, until when omega T is equal to pi. At this instant, what happens? At this instant, thyristor will be turned off. Why is that? Why is that? Do you still remember under what condition a thyristor can be turned off? Do you still remember the condition? We can turn the thyristor on. There are two conditions. First, thyristor is subjecting to positive voltage. And second, we inject gate current. So under these two conditions, when both conditions are met, then thyristor will be turned on. So what is the condition for thyristor to be turned off? You don't remember? Yes, please. We cannot control. We cannot turn it off through the gate signal for thyristors, right? But how does it turn off? How do we turn it off? It is through outside circuit, right? Do you still remember? The condition for the thyristor to be turned off is to have the current flowing through. If you have measures to have the current flowing through the thyristor to be decreased to 0, then it's turned off. So the condition is the current flowing through thyristor is decreased to 0, then thyristor be turned off. So Therefore, at this time instant, when omega t is equal to pi, I see the current flowing through the thyristor now at this instant will be decreased to 0. Why is that? Because the current, because this is a resistor circuit, the load is a resistor, right? So the current will be having the same waveform as voltage. Now the voltage is this waveform, okay? So when the voltage is decreased to 0, then the current flowing through here will be decreased to 0. And therefore, at this instant, the thyristor turn off. Okay? And therefore, this will be the waveform on the output side. Okay? You can see this will be the waveform on the output side. It's different from here, different from diode circuit. For diode circuit, you always have a full half wave. For thyristor, you can determine at what time the output side voltage is the same as input. At what time you turn on the thyristor. Okay? So that's the difference. Now, why is this called controllable or controlled rectifier? It's not difficult. It's not a difficult question. Why is this called controlled rectifier? Yes, we can decide. We can control at what time we turn on thyristor. Okay? We call that control. We call that triggering delay angle control. This angle here, starting from zero crossing point, starting from here, until when we turn on the thyristor, until when we send the turning on signal to the gate, this angle here is called triggering delay angle. This angle, I'm sorry, this is not so clear. It's called triggering delay angle. That's called triggering delay angle. Or there are other names. It's just delay angle or firing angle. It's all about the same thing. Referring to the same thing. So by changing this angle, we can actually control how much voltage will be appearing on the output side. And therefore, if you calculate the average value, of this voltage, the output voltage, that means this average value of the output voltage will be determined by this triggering delay angle. We have a equation here. This very simple equation that you can just calculate the output voltage average value. You do an integral of the output voltage, okay, and divide it by the period, 2 pi, and then you get this final equation. So you can see the average output voltage, I'm using the capitalized U sub D to represent average value. That's determined by alpha. So in that sense, this is called controlled rectifier. By changing alpha, you can control the average value of output. Why it's called half wave? That's very simple, very, very obvious, because you can, at most, you have a full half sine wave on the output side. Okay? So that's very, very simple. And actually, you can also have you can obtain all the other waveforms, either voltage waveform or current waveform in this circuit. For example, you can get waveform of the voltage across the thyristor. That's also easy. When you turn on the thyristor, the voltage across the thyristor will be nearly zero because it's turned on, it's equivalent to a short circuit. Okay? And when there's no current flowing through thyristor, it is turned off. Therefore, all the voltage it is blocking. Therefore, all the input voltage will be applied. When it is turned off, all the input voltage will be applied across this thyristor. Okay? So when it is turned off, the voltage will be the same as input voltage. Okay? This part, it is not turned on, it is turned off, therefore input voltage is applied there. Starting from here until in the next cycle, before we turn on the thyristor, all the input voltage is applied across the thyristor. So, not so difficult. Okay? So this is the simplest, as I see, simplest power converter. What happens if we change this load to be not just a resistor, but you have an inductor in series? We call that inductive load. Inductive load. I'm sorry, I have to write some Chinese for the overseas students. You can forget about that. That's inductive load. The inductive, when I say inductive, that means you have both inductor and resistor in the load. Okay? What happens? What is the difference between this situation and when you have just a resistor in the load? Can you imagine? What difference? Let's see this together. Okay? When the input voltage is positive, okay, I can control at what time to turn thyristor on. This is the same as in the resistor load. So after triggering delay angle alpha, let me just change back. This is change back to the arrow state. Okay? When omega T1, at this time instant, when triggering delay angle is alpha, okay? At this instant, I inject gate current into the thyristor, and therefore, the thyristor is under positive voltage, and I got a triggering current in the gate, therefore, thyristor will be turned on. So this is the same as in the resistor load. But what difference we have here? The difference is at this instant, what is the difference? If you compare the waveform of this page with the previous page waveform, what is the difference? Of course, because this is an inductive load, so when this is turned on, switch is turned on, the current flowing through this circuit will be always increased from zero. Because before that, there's no current. That means current zero. So when you turn on the switch, the current will again start from zero, increase from zero. But if you look at the resistor load, if you look at the resistor load, because this is a resistor, so the current will be always the same as voltage. So the current will be, at this instant, suddenly increase from zero to a certain level. The current there's a step change in the current for the resistor load.